MIT, and of course machine learning. So I hope you will get to know more about machine learning today and anomaly detection. So please pay your attention. Okay.
Okay. So I am really privileged to be here in this hall, and I am really thankful to Dr. Samim in this regard. He invited me, and I wish to share my experience rather than telling knowledge. Okay. So, and we'll see that knowledge and performance is same in the next slide. Okay. So let's see that I will be telling mostly. I will be saying about the methods used in unsupervised learning. At the end of the lecture, we will be listening about what are the techniques, and these techniques how different scientists explode in the area of structural health monitoring. Okay. So with that, I start my today's talk. Basically, I will be discussing on this topic. That is the introduction to unsupervised learning, and in this category I will be talking about data clustering, and then obviously today's topic, that is the anomaly detection.
Full screen.
Okay. And then I will be talking about very traditional unsupervised technique, quite old, but it is really very standard and traditional technique. And then I will be talking about neural model, that is autoencoder, and then variational autoencoder I will be talking about is a variant of autoencoder. And then end of the talk, as I said, that I will say that how these methods have been exploited by different scientists in the area of civil engineering, so specific to that is health, structural health monitoring. Okay. So what is learning? Okay. And interestingly, I have a project where actually what we generally we are doing. Say we are asking students to watch the video, okay, and while watching the video, we are collecting the EEG signal, okay, and after that, our conclusion is that can we really tell that from the EEG signal whether student was attentive or not. So that was the task. But in this context, what we are doing, before asking the student to watch the video, we are taking kind of test on the educational video, and after watching the video again we are taking the same test. Okay. And if there is any change of obtained marks from the previous and now, so then we say yeah, he has learned little, right? So if there is an improvement in the marks. Similarly, in some other case, let's say we are in the field of football, and some scenario we did kind of mistake, right? And if future we see the similar or some kind of scenario, and again we do kind of same mistake, then what do you say? This guy is not learning at all. Okay, so that learning is associated with your performance. Okay, if that is the scenario, that whenever someone is improving over a particular task, in a task over some kind of observation, then we say is the learning is happening. This is true for us, and this is true for the machine also, here computer, right? So therefore, formal definition is like here. An agent, it could be anything, okay, is said to be learning if it improves its performance after making observation about the environment. So after making observation about the environment is like experience. Whether from the experience, whether we are learning or not, that will be determined from the performance. If there is an improvement of performance, then we will say yes, he is learning. So that is all about learning. Okay? And very often what we say is the machine learning. So then what is machine learning? It's very simple. Machine learning, you replace the agent by the machine, or you replace the agent by the program. Okay? So then if the program is learning something, let's say you are asked to write a code for adding number from 1 to 10. Every time you will get the same results. There is no improvement. So this code cannot say is a machine learning code. Okay. So therefore, this is what is machine learning. So machine learning is the systematic study of algorithm and system that improves their knowledge or performance with experience. Okay. So that is all about machine learning. Now you must have learned other different set of machine learning algorithm. Okay, and for each machine learning algorithm, whatever it is a classification techniques, let's say decision trees, CNN, on others you learn already. So everything comes under this definition. Okay, and why it is so famous? Actually, it is not that today people are giving the definition of machine learning. So long before actually, and formalized in the year 1997 by another top guy, and this is Tom Mitchell. In 1997, he gave the more formal definition. As I said that it improves the performance, and then we will say the learning, but more formal definition as we can go through. So a computer program is said to learn from the experience. Experience means observations. Okay, and so let's say if we talk about different classification technique, observation is nothing but the training sample. Okay, so a computer program is said to learn from the experience key with respect to some class of task. Okay, so task could be, so let's say playing football. Okay, task could be classification task. Okay, and the performance P. So when we say he is improving the performance. Okay, so improving the performance in the field. So let's say in football field. So improving the performance, we cannot ask how much gate that guy got. Okay, so in a field of football. So therefore we have to have the definition of performance in the particular area, right? So let's say in case of academics, we can say performance can be the grade. Okay, CGP. Okay, so therefore we have to have this kind of definition, what is performance and so on. So then only we can say that program is said to learn from the experience, it is improved with experience, improve the performance with experience. Okay, so this guy is very famous, by the way. I think he was the first to establish dedicated machine learning laboratory, and before 1997 in CMU. Okay, so having said that machine learning and then learning could be majorly three types. Okay, so based on the feedback. So when is learning is happening, whether we are getting any kind of feedback or whether we are not getting any kind of feedback, based on that we have the two type of learning. Okay, so sometimes I relate it like so when I ask some question to the student, okay, if direct question they can easily answer. Okay, so that could be something kind of say supervised learning, and another way when we don't have any kind of feedback, so that is we call the unsupervised learning. There is another kind of learning is called the reinforcement learning. So now today's focus will be the unsupervised learning. Okay, so before speaking about the unsupervised learning, so we'll just start upon the something called the supervised learning. As we know, what is supervised learning? So one example of supervised learning is the classification. Okay, that we know, right? So what is that? The task of the classification is to assign an object into one of the predefined categories. Okay, so we have to have a category, and then you define any one of the unseen object into any one of the categories. Okay, so that is we know. And then how it works, you should have a training set. That means you should have an observation, and you should tell what is the level of this observation, what it should be told in case of the supervised learning. And then what we ideally do it, we try to find a function or a model that basically maps the category with the example, and then finally unseen object with what is called is like assign the class level to the unseen object. So that is all about the classification technique. Okay. So this is typical example of the, here we have the training set, and then we build the classifier here, we build the classifier, and then model will speak about what will be the class level of the unseen object. Okay. So there are many applications of the classification technique, as you can see, and obviously I added this one with structural health monitoring, okay, and many others. Okay. So, but problem with one slide here. So, but problem with the classification technique is it does not give guarantee that always for all domain you will get the label training data. And labeling is very difficult, right? So I saw in one lecture, one presentation, so you need to take the pictures, and if there is any crack and other thing, so you have to label it and so on. But what happened? So you are working with the known structure and other thing. So it may be something else in some domain. It is really difficult to get the label data. So you have the data, but unfortunately they are not labeled. So what do you do in that scenario? We cannot apply the traditional classification technique. So then only option you have, you apply some kind of unsupervised technique. You get some knowledge and then you try to analyze what is. So therefore this is the importance of the unsupervised learning. So here is the definition. So here unsupervised learning, known as the unsupervised learning, uses machine learning algorithm to analyze unlabeled data. Yeah, that is, I said, if you don't have the label, so what do you do with that data? Okay. So there are two major common unsupervised tasks is cluster analysis or clustering, and another is outlier detection. Actually, thing is that outlier detection is really associated with the clustering technique. So without cluster, it does not make any sense. And interestingly, while forming your objective to find the clusters, we throw out the anomaly points or exceptional point, that we will see. So therefore, these one is complement to each other in one sense, and others is actually one does not want others. Okay, so that I will show you in the next part. Now, what is cluster analysis? So cluster analysis is to discover the natural grouping of a set of pattern, points and objects. Okay. Let's say in a class we don't know that actually who came from the which part of the region, or we don't know how you are associated in professionally, so we don't know. Then we want to, based on the characteristics, some characteristics could be the age or could be anything more, so we can divide the data or we can grouping the data. Okay, so grouping the objects here. So that is the definition here is discover the natural grouping of a set of objects. But natural word is very, it's not very fits what, in a sense it is very difficult to define the natural. So some scenic view I can say it's so beautiful, someone says it is okay type. So therefore it is very difficult to have the definition of naturalness. So therefore this definition wise is very good, but we cannot work with on this definition. So therefore we have the working definition here. What is it? Clustering activity or clustering analysis is to find group of patterns and or objects we call the clusters in such a way that objects or pattern are synonym here, So in a cluster are more similar to each other than the pattern in distinct cluster. So they are saying is if the objects are within a group, they are more similar than the object from two different groups. So therefore, if we have a definition of similarity, then again easily we can work with this definition. So therefore, this is more accepted definition for the clustering than the previous one. Okay. So this is one more quite old and theoretical definition. Suppose you have a set of objects here, okay, and then what we do it, we have the set of group, here is the few sets, as you can say C1, C2, Ck. If you take the union of all C, then you will get the original data set D, and there is no intersection. Okay, intersection is 0. Okay, and then obviously if the two objects you take from the same clusters will have more similarity than the others. So this is more, but this definition has one issue. See, that is the two clusters may be the overlap in some scenario. That is in fuzzy C-mean or fuzzy clustering, we basically ignore this part. Okay. So having said that, so I will show you one very popular clustering technique, and then I don't know whether you have heard it. So that is something called K-mean clustering. Okay. So K-mean clustering basically it optimizes the sum of the squared error, defined as follows. We have, yeah. Okay. So yeah. So here what we will do it, we will find the sum of the squared error. So sum of the squared error means, say let's say you have the objects here. Let's say we have some points here. Okay. Very often what we say is actually, so can you tell me what is the average grade in particular subject? Right? Very often we say, right? So then what we stand, like we are above average or below average to identify myself. Very often you say is what is the mean, what is the average? Why do you say actually mean represents the base of the population? Okay. So therefore mean has huge importance for any kind of population. Very often we compute the mean. Okay. And then since we assume that mean is the best representation of a group of people, so anyone deviate from the mean will consider as the error. So in this context. So and then you take the square. So that is something called the sum of the squared error. Error is something how much you want deviate from the mean. Okay. So similarly, if mean is somewhere here, this guy is locating here, so this distance, and then you take the square, that is something called the sum of the square. This is the Euclidean distance we take, and the Euclid distance square. Okay. So that is for the sum of the square. And then what is the objective is? Objective to get the sum of the squared error across the, this is one cluster, another cluster, sum of the squared error across the clusters, it should be minimum. Okay. So this is basically a kind of optimization problem. Okay. You minimize the sum of the squared error wherever the mean is you locate the mean in a position wherever SSE value is SSE value will be the least. Okay. So this is what is called is the K-mean clustering. But how do you implement in scenario here? What do you do it? Select K point, because we are talking about K-mean. Select K point as the initial centroid. What is centroid? Centroid is nothing but the mean of the point. Say if you have a 2 points, let's say you have a 2 points here, one point is here, another point is here. So mean will be here. Okay. So how do you compute the mean? It is a vector, right? So you take each component divided by the number of points, then you will get the mean. Okay. So then select K centroid initially. K points as the initial centroid. So points, pattern, object, all are synonym. Why do you say the points and object same? So object means one instance. So let's say in your language, if you say we have a 10 sensor and you are getting the data in a particular instance, 10 data you are getting it, right? So that should be one instance. We'll say these 10 values basically a vector in a order, okay? And that 10 values we are plotting on 10 dimensional Euclidean space. So basically that will be the point, that Euclidean space. Here if you say is here, let's say this is age and this is weight, okay? So then age and weight, this tuple, this will be basically a point here, okay? So therefore points, objects, all are basically I am saying in the same sense, okay? So select K point as the initial centroid, means K object as the initial centroid, and then form K cluster by assigning each point to its closure centroid, and then again recompute the centroid, and you keep on doing until the two consecutive centroids are same, okay? So now I will show it one example, that's why I am skipping a little bit faster this part. Let's say we have the data set, okay? Yes.
In real data patterns provide, how we decide the A value?
Yeah, that is issues. So K-mean is like we have to have the knowledge of the value of K.
Without even on the plotting on the ground, we are seeing the loop is there here to
No, yeah, but in higher dimension you cannot do it. Yeah,
20 dimension our system not working.
yeah.
So in that case what we do?
See, we should use the domain knowledge. Okay, domain knowledge means say, let's say we assume, say crack, there will be only two type of cracks, or there may be, let's say, three type of damage. So we assume that in this breach or whatever is that case, in the structure there might be a three type of
Then we have knowledge of the output category. That
we should have a domain knowledge, otherwise you don't use the K-mean. Okay, for if you wish to use K-mean, then you should have the knowledge about how many clusters or how many different type of clusters or categories maybe. I am not saying ki you should tell that which point should be in a which cluster. I am saying is you should have a gross knowledge about that ki how many clusters there may be. Okay. So otherwise you don't use the K-mean. There are plenty of other algorithms. But K-mean is so old, as you can see, 1967. I think initial slide I showed you. So it was actually 1957, and then I think republished, and again it was published in 1981. It is so popular. Okay. Even initially when I gave the definition, so that was also it. Definition is like in the 50th anniversary of the K-mean clustering in 2010. So K-mean is so popular, so people start, if you know, anyone knows the clustering algorithm, so they will be knowing about K-mean. So K-mean is so popular and it is so easy to implement, to understand and everything, but really it has the drawback of how do you know the value of K. Okay. So this is one simple example. Let's say we have a set of points, and for easy understanding, I am considering here we have the one-dimensional data, not the multi-dimensional data. So that means we have a point 2, so it has a single feature. Okay, so that is, it's a wave point. So that means how do you represent one-dimensional point here? So let's say, so it's like a straight line. Okay, so 2 is here, 4 is here, and so on. Okay, so now according to the algorithm, what do you do? Initially we find the initial centroid. So initial centroid we consider 2 and 4. Okay, so what was next here? So select the K centroid, because we are considering there are two clusters, initial centroid, and then form K cluster by assigning each point to its closest centroid. Okay, so now we have a point 2, distance from 2 to 2, obviously first point will be in the first cluster. Then 4 to 2 and 4 to 4, obviously 4 also will be in the second cluster, and rest all points 10, 12 except 3. 3 has the distance 2 to 3, 1, and 3 to 4, both as having distance 1. So if you consider that 3 we can put with 2, and rest all will go with the cluster 4. Okay, so therefore, so we have a cluster here and then race cluster here. Now what we should do, we'll recompute the centroid. How do we recompute centroid? So we take the average. Okay, so therefore we have the what we did here is we are recomputing the centroid, that is 2.5, and then we recomputing the centroid for the second clusters. If you take the average, then you will get 16. So now what you do it again, form the cluster. So now we have a point 2.5, obviously 2, 3, 4 also will come here under 2, 3, 4. So 2, 3, 4 and rest all point will go to the other clusters. Now again here you recompute it, so that average will be 3, okay, and here average will be 8. So now again you assign the distance compute 2 to 3 and 4 to 3, obviously it will come 3, 4 will come, 2, 3, 4 will come, 10 to 3 and 10 to 18, okay, so 8 and 3, 7, so then 10 also will come here, okay, and so on. So now if you see in the next stage, what we see is, so here 2, 3, 4, 10 and rest will be rest point. So now you compute again the centroid, so it will be average will be 4.75 and this will be 19.6. So again you assign the points here, okay. So now it's like 4.75, so obviously that I think 11 also will come, okay, and then we see the next stage. So now the point is coming here and C2. So now here if you recompute, so yeah, this one and this one is same, so therefore average will come same, and then we stop it here. Okay, so this is K-mean. So why I said K-mean is one way is easy algorithm to understand the clustering approach. Another thing, there are applications where actually K-mean is applied in structural health monitoring. I saw the paper, okay. So there are plenty of algorithms for the clustering algorithm, because as you understand that method was started in long before in 1950s, and still people, the problem is so that finding similarity, and it is not the all similarity measure, any similarity measure you can develop a new similarity measure and you can come up with a new clustering approach and so on. So another clustering approach is something called clustering by first search and find of density peak. So something called the density peak clustering approach. So I'll show you one paper where this method is used for structural health monitoring or detecting the damage. Okay. So that is why I am saying here. And actually, if you see the clustering literature also, so nowadays any clustering algorithm is proposed, so that algorithm should have approach of the density based approach. So I will be talking about what density based approach, how do you compute density and so on. So here is something called two assumption here in this paper, that is cluster centers are surrounded by neighbors with lower local density. So that means here it is saying if you have a clusters here and if you have a points here and so on, that centroid point will have the highest density, okay, with compared to the neighborhood points, and there are relatively larger distance from any point. And then they are saying is, if you have a cluster here and if you have another cluster, if you have a center point here, these two center will be apart from one to another. Okay. Now just telling, I am talking about the density, right? So density of each point, right? Each point means object. So generally, how do you define the density in physics? We define the density equal to mass per unit volume, right? Exactly the same formula we use here, but in different perspective, just you see, okay? So here volume, if you see, that is, let's say in a sphere, what do we write? It's 4/3 pi r cube, okay? Okay? So these all are constant basically, okay? So now for the time being you can exclude this constant, because it will be the density will be for each point, it will be the same. So then we can say is something called R n by R cube. Okay. So now instead of taking R cube, we can take only R. Okay. So then if for all points, so we assume that is like not exactly. So we to keep it m by R cube. Okay. So now how do you compute the value of n? So point will have how we'll compute the mass. Okay. So here we go. So let's say we have a set of points and we plotted on a Euclidean space, right? So therefore, we have a set of points here, we have a set of points here. Let's say we have a point here, and then we have a point here and so on. Okay? So what is the task? We have to compute the density of a point. So let's say this point. How do we compute density here? So here what is we do here? We'll draw a hypersphere or circle in 2D or hypersphere in 3D or say multidimensional. In 3D we will say the sphere. So within the sphere centered at this point, let's say X, we'll count how many points is surrounded within the circle here. And then we count 1, 2, 3, 4. So that will be 4, 5 R cube, and this radius is let's say R. Okay, so then let's say R square. So the density will be 4 by R square. So now, what we do it, we'll keep the R same for the all points. So then there is no need to mention here. So that means we'll keep this R same here, we'll keep this R same here. So this region is more dense, as you can see, right? So the number of points within the circle determine the mass here. So therefore density we measure in terms of the number of points within the surrounded area. This is one way one can do, we can fix it. Another way we can measure the density, we'll fix the n. And we see what is the value of R. And then since it is inversely proportional, so obviously if R is smaller, then that point will have the higher density. If R is longer, say more, then density will be lesser. So did you understand this part? Okay, so we can fix n or we can fix R. So both way that we measure the density. Okay, so here we'll see that this guy how he measured. Okay, so any question, you can ask question at any point of time. Okay, so it will be much easier, and maybe if I go much faster way, it will be slowed down. Okay, so the local density of a data point is defined as a sum function. Okay, this function is very easy. Okay, this is saying, so let's say I want exactly the same thing. So I will fix this value, that is something called DC. Okay, that is DC is there in this function, right? I will fix the distance DC in this equation here, and then let's say this is DC. Okay, and then what you do it, we will compute this distance, and if this distance is lesser than DC, then I will consider this point is within the sphere, and therefore I will consider 1. So now again I compute this point, and if this distance is lesser than DC, I will compute 1, and if this point is here, so this point is above the DC, then I will consider as a 0. So that is the function here. Summation over, either it will give x of this function will give either 0 or 1. If it is lesser, if it is this value is negative, then it will give 1, otherwise it will give 0. Okay, I think this definition is somehow, yeah. X of x is a function 1 if it is x is lesser than 0. Lesser than 0 means it is within the sphere. So in this definition we are fixing what? We are fixing the R here. So R is same for the all points. Basically we are counting the mass. Mass is the number of points here. Okay. So that is the way that guy computed the distance. We will see some other way in later on also. Okay. So now they introduce, this is really beautiful because many people use this kind of density. So, but this is they computed is something called distance from a point to the other point. So they computed the distance from one point to the higher density point. So that is something called the distance. Okay. So distance generally, it is we have a one point to another point, and they consider the from one point to the higher density point. That means basically what he is trying to catch, is like, is there any cluster point with respect to the some point? Because we know this guy is located here, it has higher density than this point. So that means he is trying to locate or allocate this point with this way. So this will form a cluster. So that is these two definition he put it, and then higher density, then the point which has the highest density, how do you say? There is no higher than the highest, right? So for them, for that point, he defines the maximum distance between the one point to others. So based on this one, we just see, this is we plotted the points on 2D, okay, and you see this is it's appeared there will be one cluster here and there will be other cluster on that side, right? So here. Now if you carefully see, can you say which is the centroid of these clusters and these clusters? So if you see, it is very easy to say this one very likely will be the centroid. And here also, I don't know, but very likely it will be 10 will be the centroid. Okay. So what he did, based on the density, for each point he computed the density and distance. Obviously you may ask is how do you find that distance DC? That is really a problem. This is a drawback again. Okay. So how to find the value of the DC? Okay. So now once we get this value for each point, density and distance, now I plot it. Okay, so not I. So they plotted on the plot is something called one side on the horizontal axis we have the density, and the vertical axis we have the distance. Okay. So now if we plot it, we'll see that 10 and 1 was the centroid. It will be very far away, which has higher density and which has more density and more distance. So therefore 10 and 1 will be the point far away. Once you identify the centroid, and rest of the point you assign to the closest centroid. So that way it forms the clusters. But this algorithm is used for finding the damage. Okay, I will come later. Okay. Yeah. I don't know how much. Yeah. I am going fast. Okay. So now I will be going into the unsupervised outlier detection technique. Okay. So we'll know that unsupervised, and then what is outlier. So what is outlier? Let's say I will give you one example. So 2 a.m. night, your friend call you. So I am fine. Are you? So is this call is this call is normal? At 2 a.m. your friend is calling saying I am very happy. Are you also happy? Okay. So if you get this type of call, okay, so that is obviously not normal. Something wrong, right? So that is perfect example for the outlier. So it deviates from all other callings. Your friend is calling at 2 p.m. So yeah, it's fine. Then it's like okay, it's fine. You can proceed. Okay, you can start talking or something. But at 2 a.m. you cannot, right? So that call at 2 a.m. is something suspicious, right? So that something is something called the outlier. That means all others are normal, but there is something, this particular call is exceptional. Okay. So therefore we have the definition, proper definition. What is an outlier? So here is that. Outlier or anomaly is an exceptional object. So this call was exceptional. Okay? That deviates from the rest of the data set, from all the call you received till now. So from its really deviates. So that is something called the anomaly. Okay? So more formal definition in 1998, I think I should get here, by Hawkins. Okay? So it's more formal way. An outlier is an observation that deviates so much from other observation that it appears that the suspicion that it was generated by a different mechanism. So that point or some call due to some other issues it was generated. It's not normal. So that is the perfect definition for the outlier. So when you have some structure, okay, if there is a crack, so it is not normal actually. Okay, because all other things are fine, but there is some damage. Okay, therefore, what I say that you should not see the problem as the classification problem. You should see the problem as the outlier detection problem. Instead of, because it is classification problem, what we see, there is a similarity. Okay. So in that case, actually you can easily go with the classification problem, but this is a totally different. When you have a huge data, let's say if you have a crack different places in a particular region, so number of cracks or number of damage is almost same as the normal area, then you can go for the classification. You divide the data into two ways and there is no issues of class imbalance and other thing. You know that class imbalance problem, right? Class imbalance problem is classification is huge problem. Problem is like you have a data, say 1 million data for normal and then you have only 100 data for the abnormal. So if you apply any classification technique, you won't get the result. So in this case, only option is you should go for the anomaly detection technique. Okay. So therefore, so this is one example. Picture is very bad. Anyway, so as you can see, there are two clusters. Even you can say O3 is also a cluster. But if you observe the point O1 is like he is very sitting in some isolated position. Okay. And then you can see the point O2. Nearby point is so dense, but this guy is sitting on the very sparse region. So those points are basically the outlier points. Okay. There are many applications. Okay. Fraud detection, that credit card fraud detection. Okay. And then medical and public health anomaly detections, intrusion detection in computer networks. Okay. So that packets is coming. So maybe some packets is not is matched with all others. Okay. So this is exceptional packet. Okay. And then obviously the structural health monitoring I will show at the end. Okay. So again, is I already said I will be talking about only unsupervised technique. And for major approach for under unsupervised model is you apply the clustering technique. Okay, not obviously the K-mean. K-mean cannot detect the anomaly detection. Okay. So but there are some clustering approach like DB-scan. It was introduced in 1996. That was the first actually density based approach in clustering. This guy that I said just picked DPC, density peak clustering was in 2014. But first density based clustering was introduced in 1996. That is something called DB-scan. Okay. So there actually what is done is like this is clusters, this is another cluster, but these points they don't consider as a cluster. So basically those points they throw them. I am not interested because my interest is only for cluster. Very often we say is when in name of the data pre-processing. Okay. So especially when your objective is to identify the damage. So if any data is having damage, you cannot throw it. Okay. So therefore, in the name of the pre-processing, very often we actually remove the very important data. But if your objective to find the classification, and it is problem is also a classification problem, then it is no problem. Okay. But problem is here is you are going to do for a kind of data damage detection, but you are throwing the point which is very isolated region. But that is the interest of your interest. Okay. So so object of clustering approach is like finding the structure, not to identify the outlier point. So therefore, if you use only clustering technique, we cannot get the outlier detection. Okay, we cannot do it. And then we have the neural network model. We'll see. Okay. So so in 2000, this was also the first density-based outlier detection technique. Okay. This is also easy to understand. Okay, I am not saying much mathematics, just logically I am saying. If there is some little mathematics for variational autoencoder, but I also skip it. Okay. So here is LOF is what it is saying. For each point, it is saying how much the point could be in a grade. So outlierness, how much it could be, whether it is a point of, what is the value of the outlierness, whether it is 2, whether it is 2.1 or it is 3 or so on. And then what you do, it's, let's say if you identify, I want that there may be 10 some damage, then you identify the top 10. So that is something called the top 10 outlier. Okay. So how it is found, how it is computed? LOF is a density-based technique for finding outlier. It declares a point as inlier if it's surrounded with a dense neighborhood. Okay. Objects having a sparse neighborhood is treated as an outlier. That we also told earlier. Okay, it's not having much information here. So LOF compute the neighborhood density of each object, and the LOF score of each object act as a deciding factor. So value of LOF basically decide whether the point will be the outlier or not. Okay. In order to do what we have to do, we need to know that what is some definition of the KDs of the object, reachability distance and local reachability density. So just initially when I started giving the definition, so what I said, to identify the density, either we can fix them or we can fix the R. Okay. So earlier guy, what he did, he fixed the R. So now we will go in, he will fix the value of M, and then it will say the what value of R, and based on that its density will be decided. Okay. So therefore we need to understand the KDs and the reachability distance, which is also very easy to understand. So what is KDist? KDist of a point, KDist of an object O can be defined as the k nearest neighbor distance of the object O, where k is the positive. That means, so if you have a point here, what is the k distance? K value is, let's say, 3. So what I will do it, I will compute the distance from this point to the all other points, and then I will sort them in ascending order, and then I will say is what is the third k, what is the third nearest point, and then what is the distance. So that distance is the k distance. Is it clear? So it is like k closest distance. That is the k distance. Okay. So here is k distance, let's say 1, 2, 3. 1, 2, 3, 4. So then this point will be the k4 distance. K is here, 4. So that is easy to understand k distance. So now we will come here. Okay, thank you. Yeah, so next is reachability distance of an object with respect to the object O. Okay, so reachability distance is something here, maximum of k dist or distance from a point to the other points. So basically, so let's say I want to compute the reachability distance from this point. Okay. So then what do you do it? We'll compute k dist. Let's say k dist will be 3. So here one point, another point, and this point. Okay. And then this is the k dist point, but I want to find the k dist, sorry, reachability distance of some other points here, which is far away from the k dist. So then this distance will be the k dist, reachability distance. Okay. So here one diagram is here. Let's say we have on the right side diagram. So whenever the reachability distance comes into for definition, we have to have with respect to the other points. Okay. So we are finding reachability distance of P with with respect to O. So let's say this is the point O, we are finding the reachability distance of point P2 with respect to O. So in that case, what is the distance? That is the reachability distance of this point and then the distance. So whichever is the maximum. For P1 point, so this will be the reachability distance. Okay. So basically reachability distance is to find the distance here. So if it is high, obviously the density will be low. If it is low, then density will be high. Now once you get the reachability density, okay, so reachability density, so once you get this distance and then we get the density, then what do you do it? So local reachability density is again the same formula here, that is number of points divided by this distance. So number of points is k, nk of p is, if the k equal to 4, it will be always 4 or more than 4. When it can be more than 4, if the kth distance, there will be multiple points, you have to take all points. In that case, this value will be more than 4, more than k, otherwise always it will be k. Okay? Once we get the LRD, that is the local reachability density, then we can compute the LOF value. So LOF value is something like that. So this value, that denominator part, it will be k or above k. So this is, if you this is one thing, and then you concentrate on the upper part, that is the numerator. And numerator part, that is the denominator, LRD is always fixed for the point P, local reachability density, but it will vary for the all others points. And if you see very carefully here, you are basically comparing the density with neighbors with the point here. So I will show you the next here. Okay. And then highest LOF score of object will be considered as the outlier here. Okay. So let's say I wish to compute LOF of this point. Then what do we have to do? I have to compute LRD, that is local reachability density. So that is the, and you have to, for in that case what you have to do it, you have to compute the local reachability distance. So this distance is quite high, and you have to compare this density with the others points, neighbors corresponding density. And as you can see, this point is dense, so therefore this distance will be very less. If this distance is less, density also will be high. So then you compare the density of its neighbor with itself. Okay. So if that value is high, so then you will have the LOF value also will be high. Okay. Yeah. So now I will be talking about unsupervised neural network model. Okay. So here, actually I have seen many papers, people use even structural health monitoring also, they use the PCA. Okay. And then I will be talking about PCA, and there is a basically link between PCA and so-called in today's neural model is something called the autoencoder. Basically PCA is a special case of the autoencoder that I will show you, and then subsequently I will show you few more code. Okay. Yeah. So latent variable model is something like, say, it's mapped observation space to the latent space. What is the latent space here? Latent space is like a space where is it, like say, can you describe your friends? Let's say I started describing my friends as the height, weight, and he has the black hair, and then he has mustache and so on, and then I can say you are this, and you start talking about many characteristics, let's say 100 characteristics, but it may not be required. Height, complexion, okay, and then let's say gait pattern, how he works. If I say, so with maybe 5 to 6 features I can explain my friend. So this, instead of saying the 100 features, if I can describe the same thing with the 6 features, okay, so that 6 feature is basically here in our context we are saying is the latent variable. So we have a huge features to describe a particular image, but we reduce the dimension. So that is something called the latent variable. Okay? And there are something is called the PC and so on. So I'll show you very quickly here. So that is principal component analysis. So this slide is no mathematics, but I will describe it details. Let's say X is the data set, capital X is the data set. What do we have in the data set? We have a row and generally column, and column is basically the features. Okay? Generally we represent each column vector and then we take the transport. So therefore if we take the transport here, transpose, then we will take this value. Okay? Okay, the battery has low. No. Oh, shut down. Shut down. Shut down. अरे वो बाकी क्या shut down. Yeah, I don't know the health of my laptop as it is so bad. Yeah, I think I should install some certain other It is quite old, like I purchased in 2019. Yeah. Yeah. So basically what we wanted to do here, number of features you want to reduce. Okay. So that is the reduce is again, but number of instances will remain same. So therefore R n cross Q. Okay. So I obviously it was okay. Yes, X is observed obviously, but we have to conclude infer the Z. Okay. And obviously number of features will be lesser than the original features. Okay. And in PCA basically is no nonlinear. Okay. So that neural network is so famous because of nonlinearity. But here in PCA will do. But PCA was introduced at which year? Do you know? In 1901. Okay. So PCA is so famous. Okay. So yeah. So here what I will do it here. So let's say a simple. What we will do it. We have a point X that is actually the instance. We have the observation, and then what we wanted to do, that will be projected on lower dimension. So let's say that is the projected vector is W. So then what will be this length? This length will be nothing but the xi cos theta, because this vector is the unit vector. Okay. So what is the task? Task to identify this scalar part, okay, x cos theta, along with the W. Okay. So these two things actually we need to identify to get the latent variable. Okay. So this is one thing. Another thing is when we are projecting the, let's say that blue dots are the original points. Okay. and then we'll project on a line, because it is 2D, or on a vector, okay, where we'll have the variance is maximum. Variance means if you see the spread of the point, if you see the along the red line, so actually the object spreaded on that particular direction. So that point we have to find here. So this is PCA is doing basically the identifying the major component, major principal component, major component of the matrix. We'll see. Okay. So here what basically we are doing, we have a set of points. Let's say we have a set of points here, 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 and here. Okay. So this point, as you can easily see, let's say this is x-axis and this is y-axis. Okay. We say this is horizontal and this is vertical axis. So now, if you the spreading of this point is along this direction. Okay. So basically, we need to identify this vector. Not only that, this vector. So again, we say for this point will be projected on here. This point will be projected 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 here. Also, we have to identify this part. So therefore, we have to find the vector as well as the scalar part. Okay. So what we will do it, and say in the process we will lose some kind of information. Okay. So you are describing so details about your friend. Now I am saying you tell about only the 6 features. So obviously you will miss some of the point. Okay. So now when we are projecting this point to here, we are missing some of the information. That is, we are missing the y direction. Okay. So that is something called the residual. How do you represent this part? Let's say what we did, we are projecting this point here. And what was the original point? This was the original point x. This was the original point xi. Okay. So what is this vector? This vector is xi, because this was the original frame. Okay. And then now what PCA is nothing but we are changing the basically the reference point. Earlier we have this line. Now what you do it? We will have something like that. Now is because we wish to reduce the dimension, we won't consider this dimension. Otherwise it will have the basically the reference line, reference coordinate we are changing in case of a PC. Now here is, we come here, so this was the original vector here, this is the point. Okay. Now this is, we got it because we got the x cos theta. So this is, let's say, this is projected, let's say xi dot. Okay. And basically this distance we are missing. If there was another point here, it would be also projected on this point. So missing, we are losing this point. So if this is a vector, this is also a vector, and this is also a vector, what we can write? So we can write x vector equal to xi vector plus ri vector. So now if you know that there is some this vector is this one, this vector is this one, so this will be the resultant. So then what we can write about ri? So ri vector will be what? Will be xi minus xi. Okay, so this is something called residual. So what is the objective? We have to minimize this part. So therefore we have to have term square. So we will minimize this part. So PCA is doing the same thing. It is minimizing this error. Okay. So residual will be something. Basically, this is the original vector and this is the vector. This is the scalar part and this direction is W. So therefore we will minimize this part. Okay. So finally we will come here. So same treatment can be done some other way here. So let's say we got somehow Z and V. B is what? B is the vector and Z is the scalar part. Okay. So now we can write the at any point. Basically, what do you write? We have to identify this point, this vector. So this vector, let's say V1 could be some value, let's say alpha of I plus beta of J. So that way we have to represent V1. Okay. Similarly, V2 and so on. So then in terms of B, if we represent it and then X bar, basically what we do in here, before processing, we should shift the mean. That means so what is called feature wise, mean will be 0. So therefore we are adding X bar and all those if you do, so then finally if you continue this, what is something called some mathematics, I think you must have learned also. Okay. So then finally it will come something called the scattered matrix. Okay. Scatter matrix, and then finally this is nothing but the problem of the eigenvalue problem. So basically in PCA what you have to do, we have to find the eigenvalue of the scatter matrix. Scatter matrix is nothing but the feature to feature covariance matrix. Okay, and then finally what will get it? So xi, that is the projected part, will be x plus this one. So now we can see the PCA is something like that. Okay, so what we have, just if you go previous one, encoder will have the V transport x minus x bar. What is x minus x bar? X minus x bar is the mean shifted, and V was the actually the V was searching, that is the vector, this vector. Okay, and then that will be the part of encoder, and decoder will have the reverse thing. So therefore this picture will speak more. So you have the data x, then you apply Vt, will get the z, and from again apply you E on z, then you will get the x bar. And then basically end of the day, basically you are finding the residual loss. Same thing can be done of finding maximizing the variance. Okay. So how do you go? So all mathematics detail is fine, but what is the simplest way? So given a data set, what do you have to find? Compute the data mean, so that is very data mean and the scatter matrix. So if you have so let's say a data set of size 10 cross D, so then what will be the size of the scatter matrix? D cross D, so feature to feature. Okay. So you will have the scatter matrix, and that scatter matrix you need to find the eigenvalue and eigenvectors. Okay. When you get the compute the eigen decomposition of S, select the Q eigen corresponding to the Q largest values, and that will give you the PC. So this is same example. Okay. So as you can see, now I will talk about autoencoder. Okay. So not much. Okay. So instead of having the linear, now we will have the non-linear part. So this is, if we understand this diagram is fine. So we have the given x. Okay, we have to get z and z to x bar. To get z, we apply the eigenvalue and this one. Instead of that, we will apply the neural network model. Okay, fit for our neural network, we apply it. However, the dimension will be reduced as you see. What is the objective? Objective to get the later number of neuron will be lesser than the input. So gradually, if you have a one fit for a neural network or multiple fit for a neural network, you have a more. Okay. So this part is called encoder, and then same thing we will do with the smaller dimension. Then again we will reproduce the original vector. Okay. So now what I said, PCA is nothing but the encoder only, or autoencoder. So in PCA, what do we do it? So to get Z, we have the linear, we apply X, we apply the matrix A over X. So it's like neural network. What do we do? Very often in neural network, we use the W transpose X plus B. Right? This is famous. Right? So here is same, the W transpose X. So that is AX. And for here, to get the original vector, we apply another transformation because linear, that is matrix we apply on Z and then B. So now if you do it here in the autoencoder, what is X? First you apply Z for BZ plus A. So what is Z? Z you apply AX plus A. So now if you write AX plus A with B, so it will be BAX plus BA plus B. BAX is again matrix, so therefore you write CX, and this is also a B is a vector and BA is also a vector. You are multiplying matrix with vector, so then finally you will get the same thing, and this is the same as we said for the PC. So PC is a special case of the autoencoder. Okay? So here we say the pictorial representation, we have the 2D, then we apply GT for PC, and then we get Z, and then we get X bar. So in case of the autoencoders, so we apply, so let's say 2D, then we have the 1D, let's say you see on the last. So 2D we apply the 32 dimensional. So you have a 2D, we apply large, and then you reduce it, say 1, and then again is the same network here, and then you go to the original one. Okay, so that is something called autoencoder. So this is one example. So there is something called variational autoencoder. It takes rigorous mathematics, but what I wanted to say it here. So till now, whatever the Latin variable we are getting, so that is deterministic, fixed. We are saying this is the value. But in case of the what is called is variational autoencoder, they are not giving the value. It will give a probabilistic value for the each latent variable, and that probabilistic value is, we assume that is the Gaussian distribution. For if we want to 10 latent variable, so then what you do is, let's say 10 has a 10 features, then what will get it? We'll get the 10 pair of mu and sigma. Okay, and then from there actually based on this value it will compute the Z, and from Z to the value X bar. Okay, so this is all about the variational autoencoder. Okay, so now application of autoencoder. So yeah, this is our work, but this is very related. Why I am saying this could be used in structural monitoring. This is autoencoder. Okay, this is our work, but what is the best part is what we did. See, one thing, if you see, we have a data set, if we apply the autoencoder first, okay, and we expect that we'll get the outlier because there is no training data here. Okay, so we apply autoencoder, what do we get? We get the reconstruction error. And for the outlier point, which is far away from the normal point, we are expecting we'll get the reconstruction error more for the outlier points. Okay, now if you say interesting thing, say we have a set of points here, and we have a set of point here, and let's say we have a set of points here. Now you pass through the autoencoder. So therefore this set of points are more. So you'll get a one kind of reconstruction error. For this point you'll get the more reconstruction error. For this point you'll get more reconstruction error, and so on. So now what you can do it? The point which has more reconstruction error will be the outlier. Okay. But thing is not so easy. What happened is, like say we can consider is for this reconstruction error and for this one, so reconstruction error could be in between somewhere, as if the point is somewhere locating, that also could be the outlier, and that point also will be considered as a. This is the problem with the autoencoder. If you directly use the autoencoder, you won't get the results. So therefore, so what we did it here. Okay. So first we apply the clustering technique, entire data set. So therefore we'll have a point here. If it's some point here, we'll have a point here. So now within a cluster, we identify using density peak or some other clustering, we'll identify within a cluster is there any probable outlier points up there. So then what we did it, we exclude this probable outlier point and train the autoencoder. Now autoencoder is purely trained on the normal points. Okay. Once it is trained, then again you feed the entire data set. So now the point was trained on the normal points, so-called normal points. Now if you send the all points which was not trained, the point on which it was not trained, very likely will give the high error, and that point will be considered as the outlier point. So therefore we apply the clustering technique, identify and remove the probable out. We are not saying the final. These probable outlier points, and we say these are so-called normal points. So in the removing process, if you remove some normal point, it does not matter. But important is that it should go the probable outlier points, because we want the autoencoder should be trained on the normal points. So therefore, if the abnormal points come, it can easily identify it has a error, what is called is reconstruction error. So that point will be the normal, abnormal points. Okay. So I can skip this part here. Again, yeah. So finally, this is coming here. Say unsupervised structural health monitoring framework. So they have excessively used, because this is related with vibration related bridge and other things. So they collected the data, and that data is a sequence data, like signal. Okay, I think you will be knowing more. So therefore they use the traditional technique, okay, wavelet and other techniques, and they pass through the upper part is something called variational autoencoder, and then variational autoencoder detect the damage. Okay. So maybe variational autoencoder is something like that, as I already said. Okay. So this is the paper published in 2023. I think you can say how good the why is the journal name? I think I missed the journal name. I think reliable engineering or something. Reliability engineering or something. Yeah, that is it. So this is all details. Okay. So we have the data here. Then we are fitting with VAE, variational autoencoder, and then compute the L indicator. Here is L indicator is nothing but the reconstruction error. Okay. So we got the reconstruction error, and then you will get the many faults also. Okay. Because as I said, no, it will not be the perfect. Okay. So nothing is perfect. So then what they did it, using whatever you got it, again they are passing to the another variational autoencoder, and based on the grade they are saying is how bad it is, and then they are putting is, let's say, 10% or 20%, so on. So that is all about the diagnosis. Okay. So another paper you can see on the here. I don't know how much is related with your work, but it's your area, that unsupervised deep learning for structural health monitoring, published was big data and cognitive computing. Okay. So this was from I think Brazil or somewhere, Italy. Okay. So what they did, the proposed approach based on the unsupervised deep learning algorithm will aim to establish the reliable so this is all about the railway bridge data acquired from the physical sensor, and then the physical sensor was positioned in historical tower of Ravenna, Italy. Yeah, this paper was from the Italy. Okay. So again they use the one simple autoencoder. Okay. So this is like only one hidden layer there, and then also is they use the variational autoencoder. Okay, to identify the autoencoder use. Yeah, I think I talked about this one, right? The density peak clustering, DPC. So how nicely they use, I just read yesterday, okay, that paper, how they nicely use for identifying clustering technique, but identify the outlier so nicely. Okay, so let's say this is the point, DC, again they use the same term, DC, they computed the density, but here they change, okay, how they change so nicely. So what I said, within the DC distance, how many points will be considered as the density? But they use some different tricks. On the right side function they use to compute, it should be smooth. So they use this function to compute the density, not directly. So they use, that is the negative of Ex part, this one. So this will be little smooth, I feel. So they use this part for the density, but distance function they kept the same way. So once they compute the density and distance, now they use the decision graph. Okay. So this is I think decision graph is here. Okay, they use the decision graph. So using decision graph, they identified the centroid, that is 1 and 10. Okay, and they assigned all points to these two clusters. Okay. Yeah. So now they are 1 and 10. But their task is not to identify the cluster. Their task was to identify the outlier point. They said in the paper is novelty point. Novelty. So how they nicely did it? See, within a clusters, now they identify the clusters. Within a cluster, they identify the point which has least density. Obviously, very likely that point will be the outlier. So therefore, there is a chance for 29, 30, 28, even 27 will be the outlier point. Another interesting thing they did, that is I am very much impressed. So we have two clusters. Okay. Now the border region. So there is a high chance that these 2 points could also be, because this is the border region. So they identified the border region points and they find the density. So therefore, they identified this border region. For identifying border region, they use the simple distance measure. Okay. If the point, so let's say this point originally, let's say point originally was 25. Okay. It was part of the cluster 1. Now they compute distance from 25 to 10. If this distance is within the DC, okay, that point should have come with 10. So therefore, this is something, the point which might be actually the border region point. So locate that border region points, and then they conclude the density also, and they say these are the points for the anomaly detection. Okay. So this is bit old because it was I think 2018. Okay, that time people did not start using even in neural network model so much. Okay. I think this was the survey paper. So I don't know. You can say how much good this review sensor to direct sensor. I don't know how much good this one. Journal I don't know. So here they surveyed is the total article and the work on the deep learning method. If you see that half from the 2020 only. Okay. So and again 2023 paper was published, so you can leave 2023. Again it was down for 2022. And then maybe best way to apply the traditional and then deep learning technique. And these are the few papers where they use it. Okay. Okay. So maybe I stop here. Okay.
So if you have any questions, please feel free to ask.
Yeah.
Specific question.
What will you put it?
Confusion matrix and logistic regression. With regression models and confusion matrix, you can use for
Confusion matrix for evaluating the method. Okay, so it is a evaluation technique. It's not the detection technique. Regression is a detection technique, but how good your detection method is, for that obviously you can use confusion matrix. Okay, so it is a evaluation. So that confusion matrix is used in many domains. Okay, even corona detection also people use, right? So therefore that is a detection method. Okay. And regression, problem with regression is that is the label data. So that is a supervised learning. So when you have a label data, why you should go for the unlabeled data? Because unlabeled data always will give lower performance than the labeled data. So if you have a label data, then you should go with the label data. But if you don't have sufficient label data, then you can mix it. Okay. More question?
Any other question? there will be another session in second half from 3 p.m. Okay, so you will be able to interact again with.
Yeah, but I won't teach anything here. Okay. So